2022 question number 5. This one is about Chinese knots, and it's mostly organic chemistry with a little bits of other things thrown in. So we have a part of a synthetic route here, and we're asked to draw the structure of A. So this is the molecule we're trying to make. We're starting with A, and we've got concentrated sulfuric acid and concentrated nitric acid. Very, very standard reaction mixture. Okay, so you should know that this is the nitration of aromatic rings. So basically these two here are going to put on this NO2 group. So A is just going to be this without the NO2 group. That's just something you need to know. It comes up all the time. So definitely worth just being aware of that for the free mark in the back pocket. So that's that. And then it says to draw the structure of the active electrophile formed when A reacts to form 3-fluoro-4-nitrophenol. So when A reacts to form this, what is the electrophile? In other words, what do these two combine to make that then adds on as NO2? And they even tell you that it's an electrophile, so it's probably going to be positively charged. And it's worth knowing that HNO3 and H2SO4 combine to form NO2+. But you're asked specifically for the structure, so you should be drawing it out. So I'm going to draw it out as a Lewis diagram. I've got 5 electrons from nitrogen, 12 from oxygen, 17, but I lose 1 for the positive charge, so that gives me 16. So 1, 2, 3, 4, let's just go with double bonds, 5, 6, 7, 8. So that's all of my nitrogen electrons complete, and I've got 8 electrons left, so I can just put them in like that. And don't forget the positive charge. I think that'll be fine. The mark scheme tells you to just has it as an NO plus. But the main thing I think they're looking for is that it's linear, so I think either of those will be fine. Okay, then we're going to have the alternative way of approaching our first compound from B, and you're told that elemental analysis of B is carbon, hydrogen, nitrogen. This reaction here with the copper catalyst and the potassium fluoride is just going to add on the fluorine. So I've got my carbon, I've got my hydrogen, I've got my nitrogen. The missing is the oxygen. So it's just a simple empirical formula calculation, but also with oxygen. So I'm going to have my carbon, my hydrogen, my nitrogen, and my oxygen. So 51.81 divided by 12.01. My hydrogen is 3.62 divided by 1.008. Nitrogen is 10.07 divided by 14.01, and then my oxygen is everything that's left over. So it's going to be 100, take 51.81, take 3.62, take 10.07, leaving me with 34.5 divided by 16.00. So I work all those out. Divide that by 16 gives me 2.16. 10.07 divided by 14.01 gives me 0.72. 3.62 divided by 1.008 gives me 3.59. 51.81 divided by 12.01 gives me 4.31. And then I just work out the simplest whole number ratio, divide them all by the smallest one. So if I divide that by 0.72, I get 6. 3.59 divided by 0.72 gives me 5. That's 1. 2.16 is going to be 3. Yeah. So C6H5NO3. Now, what did the question actually ask me? No, it asked me to draw the structure. Oh, well, I mean, I sort of said that. So you wouldn't actually need to do that at all. You know, if you know that this is just adding on the fluorine, you can just go ahead and draw that, because that structure I mean, I guess the empirical formula is there just in case, but it is possible to do it without the empirical formula. Like that. Okay. So then our 3-fluoro-4-nitrophenol is converted into compound D. So through C. All right. So first we're going to draw the structure of C. Now, this is where, obviously, if you're confident with these organic reactions, you'll know that which part of this molecule is going to react with which part of this molecule. Okay, so if you've got more experience with organic chemistry, you'll sort of know what's going to happen. But like normal, if you don't, you've got to look elsewhere in the question, see if you can get any clues for what's going to happen. And if you look later on, we have this situation. Okay, so this is what we're aiming towards, this complicated mess. All right, but if you look here, you can see that I've got this thing that I'm reacting here. I've got this 1, 2, 3, 4, 5, 6, 7 carbon chain with a double bond. 1, 2, 3, 4, 5, 6, 7 carbon chain with a double bond in. And then it's bonded to oxygen and the benzene ring and then 2 nitrogens. So we can start to see that it must be the oxygen reacting with this end here. And then I'm still going to have my nitrogen at the end, and my fluorine is probably going to be replaced by another nitrogen at some point. But let's just do this first step first. So all that's going to happen is the oxygen is going to come along, and it's just going to do that reaction there. Okay, so the clue is always later on. So we're going to get, because it's obviously there's 2 ways of really being able to do these questions. One is just having immense organic chemistry knowledge, but not everyone, but almost everybody's not going to have that. So you need to have other ways of being able to do the questions, and they will help you to be able to do that. 1, 2, 3, 4, 5, 6, 7. Okay, so that's C. Then we have D. Okay, and again, it's sort of like, well, where is D going to react? Well, I did say just now, didn't I, that you can see I've got my oxygen, I've got my carbon chain on it, and I've got nitrogen here and nitrogen here. And now, even more importantly, is that this nitrogen is bonded to R, which is the R group here. So it's like this nitrogen, this one, is the N in my nitro group, and then the other nitrogen is this nitrogen that I'm introducing. And you don't need to worry about it. I've got it in a slightly different orientation. Okay, but you can see that if I go from the oxygen, I go 1, 2, 3 carbons round. So I'm going to go from my oxygen, I'm going to go 1, 2, 3 carbons round. So I really am just going to be replacing this F here. Okay, so I'm going to do that. 1, 2, 3, 4, 5, 6, 7. You've got to count it, all right? Because you will get penalised if you get this right, and if you get everything else right, but your carbon chain is 1 carbon short, you're going to lose the mark, I'm afraid. And that's NO2, and then you're going to have N, R, and H, like that. Okay. All right, I think that's pretty straightforward so far. So then we have compound D is converted into the organic strand in 3 steps. So D, step number 1, step number 2, step number 3. Okay. And we are asked to work out what E is. Okay. So just remind ourselves of what D is. D is this. Okay. And we're going to this. Now, in E to G, I've got this compound here, that thiazolothiazole. Sorry, my pronunciation's not excellent. And it's good to identify where this is adding. And you can see it's adding on over here. Okay. So then you need to think to yourself, well, if this step is doing this bit, then what's this step doing? And now all of this bit I've got in D. Yeah, that's all still there in D. So the D to E step is this bit. So it's adding this on here. Okay, it's adding that bit on. And you can go further and you can say, well, look, if E to G is just adding this bit on, then E is just going to be this final thing, just with that taken off. Okay, so let's just do that. All right, so let's just have E. So it's like this is one of those cases where working backwards is just as, if not even more useful than working forwards. So I can just, you don't need to know what happens here. Oh, sorry, what happens here. Okay, so we're going to go along here. And then none of this chemistry, this is complicated chemistry, right? But I don't need to worry about it because, their idea is that they're not testing you on your knowledge of these obscure chemical reactions. They're testing you on, can you work the problem? Can you, using the information that you're given, find the solution? 1, 2, 3, 4, 5, 6, 7. And then what goes over here? Well, it's just this bromine, right? Okay, now you don't need to know what that reaction is. If you're interested in what the reaction is, you can go look it up. Okay, I don't know what the reaction is. It's one of these nitrogen ones that I know nothing about, so I'm not going to worry about it. And then reagent G. So then I go from this to this. Right, so what on earth is happening here? So if I start from this end, okay, I start from here and I start from here, you can see they're the same. And I go all the way along until I get to here. Okay, and then it's the same on this side. I go all the way along until I get to here. So the G reactant is just this thing that I'm putting in the middle. All right, so I'm going to draw that. So it's this pyridine ring with a tertiary amine off the bottom of it, like that. And then what happens is, this carbon here bonds to this carbon up here. Is that right? No. What am I talking about? This carbon here, this one, bonds to this one. Okay. Now, that's not just going to happen by itself. We have to have a leaving group on here. This is going to be some sort of substitution reaction, and you need a good leaving group. Now, this is the point where, if you know it, you know it. I don't know it. Okay, I don't know what would be a good leaving group here. A more experienced and more knowledgeable organic chemist would. Usually they'd give you a clue. I feel like here they haven't really given you that much of a clue. But there is one which is sort of, I guess it is a clue actually, what I'm talking about. From, in the step from E to G, this double-ringed thiazole thing here reacts with E. And it does so where there's a bromine leaving group here. So the thiazole, this double ring thing here, adds on here. And they've got a bromine. So the best bet, because remember what we're doing, I just said, is we're going to now bond this carbon to the other end of that double ring system. It stands to reason that the best thing to put would be Br. I think once you've identified that there has to be a leaving group, and that's just comes with a bit of a feel for the chemistry. It's not much effort to work out that it's probably going to be bromine. Then we're given some NMR data. Fantastic. I love a little bit of NMR. In the spectrum of D. Now D, you'll remember, the signal D is this here, this thing, and it says the signals from the alkyl group R are as follows, and then it wants us to draw the primary amine that is used to synthesize D. Okay, so the way that I would do this is I would just try and work out what the primary amine is based on this data. Okay, so I'm going to have a primary amine, H2N, and then there's going to be a carbon chain, and then we're going to have a doublet of 2 hydrogens, 1 hydrogen, 2 hydrogens, 6 hydrogens. Okay. Now I need to be a little bit careful here, because this data isn't going to quite work for the primary amine, because it's saying that it's here. So in the R group, I'm going to have 2, 3, 4, 5, and 6 is 11 hydrogens. Okay, that's fine. So we can work with that. So basically, I'm going to have 11 hydrogens in here. All right, and I'm told that I've got a doublet of triplets, 2 hydrogens and a doublet of triplets, which makes me think. Let's have a look. Well, I've got. What's the easiest one to do here? Because you can see it's just sort of thinking it through yourself. So 6 hydrogens. 6 hydrogens is probably the easiest thing here, especially if it's a doublet, because what that means is I'm going to have an R like that. Okay, because then it's a doublet. So these are CH3, these are CH3. So these and these are the same. That gives me my 6. And then they're split into a doublet by this one here. All right, so I'm expecting to have that. And then that also gives me the 1H multiplet, because that's the 1H, and it's split into a multiplet by all of these. All right, which then leaves me with 2 others. So I can expect to have 2 environments in the chain. So there's going to be 2, 2, and then I have my group like that. Okay. And that can be 11 hydrogens, 3, 6, 7, 8, 9, 10, 11. Yeah. Okay. I'm just thinking now. This would be a doublet of triplets. Doublet from this hydrogen. Triplet from these 2. And then but I've got doublet of triplets, which means that this must also be a doublet of triplets. Now, I don't quite know enough about NMR, because essentially what we're saying is here, instead of R, I'm going to have this, this, this. I've got that, right? So then the CH3 and the CH3 gives me my 6 hydrogen doublet. This hydrogen gives me my 1 hydrogen multiplet. These 2 hydrogens give me doublet triplet, and these 2 hydrogens give me doublet triplet. Okay, I didn't think that it would be split by this one through the nitrogen, but like I say, I'd have to look it up whether or not that's allowed to happen. But anyway, that's what we get. Okay. So then, on the structure, so atoms in each strand coordinate transition metal ions to form the 3x3 grid. So this is the strand. This is now the strand, and it's going to form a 3x3 grid. So essentially, what I'm going to have to do, I guess, is if I represent this whole molecule as a strand, I'm going to have 3 of them. One way and 3 the other way. Like that. Okay? And the way that these intersections are going to work is because they coordinate to transition metal ions. Okay, so each transition metal ion is going to coordinate to 2 strands, because each of these intersection points is 2 strands, which means that on this organic strand there is going to be 1, 2, 3 places where the transition metal coordinates to the organic strand. And it says draw in the place of the metal ions and show which atoms coordinate to each metal ion using the style over here. They don't say that it has to be bidentate though. Okay, and if we look, we needed to join at 3 places. Now this junk on the end we're not going to worry about. You know, the key is you need to have lone pairs, right? Lone pair, lone pair, lone pair. And you can see it happens, these 3 nitrogens come up in 3 places. Alright, so it's going to be M. Just do exactly what they've got. That. M. And M. Okay. And so that would give me 1 strand across, and then 3 other strands would come down here, down here, down here. Alright? And so then it says, what is the overall coordination geometry around each metal ion in this 3x3 grid? And I said over here that each metal ion coordinates to 2 strands, and each strand is doing it, it's a tridentate, which means that overall this metal ion is going to have 6 lone pairs bonded to it, which means it's going to be octahedral. Okay, and if in doubt, if it's a metal, just go with octahedral. All right. You know, that's the kind of question that you should flick through in the last like 30 seconds, and you know, just tick one. And if it's metal, just tick octahedral. All right. Okay. Then we have this formula of the metal salt added to form the grid can be written as NX2 6H2O. So it's a +2 cation from the first row transition metal, so that limits us to these guys here. And we've got a tetrahedral anion of charge -1. Upon shaking the salt in aqueous sodium hydroxide, a green precipitate is formed that turns, upon standing, turns brown. Okay, so it's like it's ion testing, right? And this really is know it or don't know it. Luckily, I know it. That iron is Fe2 plus is green, and then when it oxidizes, obviously it turns brown. You know, Fe3 plus. You know, the same thing that happens when it rusts. So no issues there. M2 plus is Fe2 plus. Okay, and then the more interesting problem is upon shaking the salt in upon gentle heating the salt, there is a 32% loss in mass. This confused me for a little while because I was thinking, oh, the loss of the mass, is that some part of the salt? But then no, I realised that they just mean the water. Okay, so you heat it up, and the water utilization accounts for 32% of the mass. And then the anion X- contains 2 different elements, neither of which is oxygen. So we're going to be able to work out the identity from the fact that we've lost 6 times H2O is 32% of the mass. So we can work out what the total mass is, and then we can take away the ion and work out what the anion is. But can we first, before that, can we start getting some ideas of what kind of thing is going to make sense for X-? So a tetrahedral anion of charge -1. So, you know, the first thing that I thought when I saw tetrahedral anion was I thought NH4 plus. Okay, because I think tetrahedral ion, and I think NH4 plus is the first one that comes to my head. Obviously that can't be right though, because that's a cation. So then I think, okay, well, what anion is there? And then I sort of looked at the periodic table, and obviously I have to be looking over at this region over here, and it can't contain oxygen. Can't contain oxygen. And after a little bit of thinking about it, I remembered that boron and aluminium, they can form, because they've got incomplete octets, they can add on an anion. So BF3, for example, BF3 can become BF4 minus. Alright, so then I started thinking, alright, so it could be something like BF4 minus, BCl4 minus, AlCl4 minus. I don't know what else you could have, aluminium hydride or something crazy. Alright, so it's going to probably be something like this is what we're looking at. So let's then go ahead. So if I know that 6 times 12.01, nope, there's no carbon in water, 6 times 16 plus 1.008 equals 18.008 times 16 gives me 288 point. What am I doing? That's not the right number. Let's try this again. 18.008 times 6. There we go, that's a sensible number. 108.048. Now that is 32% of the total mass. So the total mass is going to be 108.048 divided by 0.32. Divided by 0.32 gives me 337.65 grams per mole is my total mass. Okay, and then we do 337.65 minus 108.048 minus the mass of iron 55.85 108.048 minus 55.85 gives me 173. And that is x2. So easy thing to do now is to forget to divide by 2. Divide that by 2 gives me 86.9 grams per mole. And now you've got to work out what it is. So based on what I had earlier, it can't be an anion with chlorine in because 4 chlorine is going to be too much. So what if I do 4 19s? 4 times 19 is going to be 76 plus the 11 from boron is going to give me 87. Okay, so yeah, BF4 minus. Okay, which I think is a nice question. That's a nice 3 marks, right? And then we have this final bit. Okay, so they do this. They give you this bit of information about the reaction. It's not important. Okay, the important thing is that they have this situation here, and then they join together different ends, and they give you 4 options. This has nothing to do with chemistry at all. I don't. It's sometimes actually I really like this question. I think it's kind of fun, but I do wonder how they come up with it. This is almost like, I don't know, if I'd done a maths degree, I'd know if it's like topography or something. Knots, I know mathematicians love knots. But anyway, we've got these 4 possibilities, and it gives you 4 things that they can do. So, they make these connections. All you've got to do here is just got to draw it on. Right, so they connect 1 and 2. Connect 1 and 2. Connect 3 and 4. Connect 5 and 6. Connect 7 and 8. Connect 9 and 10. Connect 11 and 12. And what have I got? Well, you can see that if I start at 1, I go all the way round, and this is sort of the point of the Chinese knot, I think, is it's all in 1 strand. So that's a Chinese knot. Okay, so that's a Chinese knot. Now the problem is I needed the same thing again for 3 more, but I haven't got this picture anymore because if I try and start drawing over the top of it, it's going to get really messy. But that's okay. All I got to do is just make my own version. 1, 2, 3, 4, 5, 6. And then I join 1 and 2, which are these two. 4 and 5, which are these two. 6 and 7, these two. 8 and 9, these two. 10 and 11, these two. And then 3 and 12 remain unjoined. So what have I got here? Well, if I start, let's start at 12. I go down along here, up along here, around, down and along here in one line. But then I've also got this individual ring here. So I've got two different things going on. I've got a linear organic molecule and I've got an individual ring. Okay, let's do number 3. So I'm going to join 1 and 2, 3 and 4, 5 and 6, 8 and 9, 10 and 11, and now 7 and 12 remain unconnected. So again, what have I got? Well, if I start here, I go along, around, and along, and up here, and that is a linear organic molecule. And then you can see I've got this ring and this ring. So I've got 2 rings. Now the decision you have to make is it what 2 individual rings or 2 interlinked rings? Now I don't think it's possible to have 2 rings and not have them interlinked, because you can't quite see it on my printout here, but this strand here goes under, over, under. This one goes over, under, over. So I think, you know, if they cross, they have to be interlinked. Yeah, because this one's going over then and under. Over then and under. Alright, so as well as my linear organic molecule, I've also got 2 interlinked rings. And then the last one. I've got 2 and 3, 4 and 5, 6 and 7, 8 and 9, 10 and 11, 12 and 1. Which is basically the same as 1, but everything just shifted along by 1. And you can see by following any place along here that it is just going to end up all in one line, which makes it a Chinese knot. Very nice.